Hello and welcome to the debate, where we'll finally settle the age-old argument of the shape of the Earth. On the left we have Team Globe, freshly brainwashed by their Masonic University education, and on the right we have Team Flat, with their degrees in woke studies at the School of Life. Please put on your tinfoil hats and enjoy the show.
Question number one is, why doesn't the artificial horizon on a plane roll backwards during straight and level flight?
Yeah, I'll take this one. Yeah.
So, over to you, boys.
Thank you. So this is terrifying. Okay. So basically, the main thing to take from that is straight and level flight. What is meant by straight and level flight? Because I imagine when a pilot's in his cabin, they try and maintain a constant altitude. So while on small scales, their flight path seems indistinguishable from straight, like a straight line, is actually going to be, on larger scales, curved, much like the Earth is curved on larger scales.
Yeah. That was the answer.
Yeah.
So what you're saying is, again, on most of these answers, you seem to be assuming every time a priori that we live on a ball, but the actual facts are that a plane flies level and the artificial horizon doesn't dip. It doesn't have to dip its nose down every minute or so to follow the curve. You're assuming always a priori that we live in the heliocentric system. If we assume that we're in a small universe and that the plane is flying level over a level plane, we're still going to get the same results. It doesn't roll over as it rolls over the curve.
I think you're slightly misunderstanding the question. Imagine a plane before it takes off. Yeah.
Okay.
It's got a gyroscope in the artificial horizon. Okay. It spins that gyroscope up to get the reference of the ground. Okay. Now, if that plane starts going over the curve of the horizon, yeah, the gyroscope will stay upright. It's rigid in space, so it will stay upright as the plane rounds the curve of the Earth. So the artificial horizon will roll backwards, yeah, but it doesn't. It stays straight and level. The plane is not going over a curve, but flying over a plane.
I don't see how it can be independent of gravity or anything like that if it relies on the horizon.
No, it doesn't rely on any horizon. It's rigid in space. That's one of the properties of
I don't think it's unaffected by gravity.
If everyone's okay, I'm going to move on to question two. Yeah. If gravity is the only thing holding the air to the surface of the Earth against the tendency of a high pressure system to escape to a low or negative pressure, then when air is heated and so is less affected by a gravitational pull, shouldn't it then succumb to the force exerted towards a region of negative pressure? What?
So basically, you're asking why air can be heated and escape, basically. Yeah? There's two competing forces. There's gravity pushing downwards, and then there's a thermal pressure of air pushing upwards. The laws of gravity dictate that the air pressure is going to be higher at the nearer the Earth than outside. So if you got a heated column of air that would rise away from the Earth, as it would rise, it will become less dense as it's less affected by the gravity as it will be at a greater distance, and thus have a lower thermal pressure pushing upwards. So that system stays in that equilibrium state. And that's called the hydrostatic equilibrium, and you can read a lot about it.
Okay, let me get this right. Okay, so we've got a state of equilibrium.
Yeah, gravity pushing down, thermal air pressure pushing upwards.
Well, when you say thermal air pressure, what I'm seeing is you've got a vacuum next to a pressurized system, okay? And we always see, hang on, we always see where there's high pressure next to low pressure or zero pressure, a movement from between one and the other, okay? We can do an experiment. If we had a container and we evacuated that container less than the vacuum of space, yeah, and we pierced the bottom of the container, what would happen?
Air will rush in to balance that out, basically.
And it will fill it up and balance it out?
Yeah, because it'll equalise locally, basically.
So how can, on the surface where it's the gravity strongest, with a vacuum that's weaker than space, how can it work down there
because
and not work up there?
It's unfortunately not analogous, because it's not a really high pressure system against a really low pressure system. It's a gradient. So as it's really dense at the surface, and then that density decreases and decreases towards the vacuum of space. So it's not there's no warp at which there's
but there has to be a
vacuum.
boundary condition, right? The few air molecules at the top will immediately go out to space, right? They'll immediately.
Yeah, no, it's not a negative pressure system. It's an incredibly low pressure system.
We always see high pressure goes to low.
Yeah, unless there's forces acting on it, and that is gravity that's acting
Right,
on it.
but okay, what I'm saying is,
Earth.
as soon as the air gets heated at the top, it rises.
And becomes less dense, then has less thermal pressure. So,
okay, so
that equilibrium state balances it wherever it is, and brings it back into that equilibrium. That's why we don't want it losing atmosphere.
So where can we see an example of this idea of thermal pressure demonstrated on Earth?
I can't give an example right now.
I just want to make one point on this. I think what we're describing, when the sun rises, heats the air rises, and as you say, it's an equilibrium system, all the air rushes in. I think that's how we get the Coriolis effect. No need for a rotating globe to create it. It's exactly air pressure, air difference in temperature, difference in pressure, and the system kind of, being an equilibrium system.
It's a good idea. It's a nice idea. It's something you have to prove empirically.
If you can't demonstrate it, how can we see, no, it's real?
Well, if you have air particles in a container and then you heat the air particles, the pressure is going to increase as the temperature increases. That is thermal pressure. It's the kinetic energy of the particles and their collisions against the wall of the container. As the temperature increases, they have more energy, more collisions, more pressure.
So you'd agree we're in a container?
Again, there's no set boundary. It's that gravity holds our atmosphere to our planet.
But the scientific definition of air pressure is that measured within a container. So what should it be?
Is it?
No.
Do you want to take yes? Okay.
If you imagine we take a random part of our ocean, we're underneath, take a random bit of water, you make like a dotted circle and there's a bit of ocean there. That part of ocean, assuming there's no waves and assuming there's no motion, is staying in that one place. Now, you'd think gravity would make it want to go further down, but it doesn't, it stays where it is. That's because there's an inherent pressure taking place there due to all the water surrounding it. So because of that, you can imagine if we're using arrows like in basic mechanics, you've got an arrow going down, and then you've got arrows in all other directions and an arrow going up. That's the up arrow is the pressure, and that's what's balancing it, keeping it there. All these ideas can be explained with pressure and gravity in this way, and it does not require a container to do it.
I just want to make a question, but all these from the early 50s until our days, the space agency launches a lot of rocket space. That don't break the equilibrium?
So as a rocket leaves the atmosphere, it doesn't leave a hole behind. When you take into account how big this rocket is compared to the size of the atmosphere, it's very tiny. It will essentially punch a hole through the atmosphere, but that hole will reform immediately afterwards.
And somebody measured that or see that? Just a question. I mean, for me,
I'm not a rocket scientist. So
that's what our theory predicts, basically.
Yes.
Yeah, that's a prediction we can make with our theory.
I imagine that something like that is factored into during launches as well.
Breaking news. This is from phys.org, from our website. It says, Earth's atmosphere is leaking. Every day, around 90 tons of material escapes from our planet's upper atmosphere. Yeah, so it's supporting what I'm trying to say. If 90 tons of material leaks away every year, or every day, yeah.
Don't breathe anymore.
So, yes, save your breath, everyone. So, all of a sudden, when that atmosphere leaves, then you've got a new layer of atmosphere, the new lower level of atmosphere, and now 90 tons of that leaves that day, and then so on, until there's no atmosphere left.
Yeah. This is the model that we have one set atmosphere, and once that air is gone, it's gone forever. We are constantly producing gases. I've produced quite a few today.
Number 3, so wrong. How would you explain light slowing down and hitting a denser medium and speeding up after leaving that medium for a less dense medium when the law of conservation of energy prohibits such observations?
There is a quantum mechanical explanation to this, but I don't think we have time to go into it. I don't have a whiteboard. So the way that I picture it is that actually light traveling is essentially it hits an atom. That atom absorbs the photon. Electrons within the atom are excited to a higher state, and then they drop back down, and the photon is re-emitted. So here in the air, we have a much less dense system of these atoms than we do in a table. So once you shine the light into a block of glass or something, it's then being absorbed and re-emitted by far more atoms. So it appears to be traveling slower. In fact, it's still traveling at the speed of light.
Somebody ever see an atom? Is real evidence of the existence of the particle called atom?
So in terms of directly seeing an atom, it's impossible. We can kind of indirectly infer it through things like electron microscopy and things, where you look at the interactions of electrons with these atoms and build up pictures of them. So yeah, in terms of seeing an atom, we can't do it. In terms of knowing that there are things there, as far as we know there are.
So it's like exoplanets then. You can't see them. We're just guessing what they are.
You can see some of them.
Oh, really?
Yeah, you can actually direct image some of the closest ones.
Oh, really?
Yeah.
With recent technology, yeah.
Can you calculate Can you calculate any planet's orbit based on gravity/mass alone when using all masses in the entire solar system and get a result matching the prediction algorithms of the proposed elliptical orbit of any planet? I couldn't say that backwards.
I can try and sum up the question to how I understand it. So the idea is that using something like Newton or Einstein's gravity, can we accurately predict the orbits of the planets in our solar system? I got that one?
Yeah.
Cool.
Short answer, yes, pretty much. We have a very good idea where all our planets are going in our solar system. We know where they're going to be, and we can continue to predict where they're going to be for the next 500, 600, 700 years. That's because it's based on really quite a simple system of just pulling in certain directions at certain velocities. We didn't actually discover Neptune and Pluto straight away, and yet they were predicted because we found that due to the way the planets are orbiting in our solar system, Uranus, we would expect them to be there. And when we looked for them, we found them. We would not continue to follow these if it weren't for their predictive capabilities. The same laws help us work out when we're going to have a solar eclipse and a lunar eclipse. It's because they're simple models and it's very easy to do.
I just wanted to make a little point because this is the second time that you kind of waxed lyrically about Newton. Newton's theories didn't explain everything. Now, Newton wrote a huge tome basically to describe his theory of gravity. Now, when Einstein came along, he gave a completely different interpretation of what gravity is. So that means everything Newton produced was bullshit. No, bear with me, yeah? If he wrote all this calculus and came up with a theory that didn't quite match, what we observe, yeah, which means it had no relationship to reality, and Einstein came along and gave a completely different interpretation, which apparently does match up. That means that whole book is bullshit. He made it all up.
I actually totally agree
Yes,
with
it's
you.
the right answer.
Yeah, Newton was wrong. Demonstrably wrong, in fact.
And yet it stood for 400 years.
Yes, but you can still apply his calculations to kind of most, certainly everything on Earth. Quite a lot of bodies in the solar system. His calculations work, well enough. Sure. He was wrong. This is why I say that nothing is ever fact. That things are just theories until someone comes along and proves them better. I'm sure, maybe in another century, 2 centuries, or whatever, someone might come along and say.
The world's flat.
And say that Einstein's theories of relativity are wrong and prove those. But at the moment, that's the best we have, and that's really how science works.
Yeah.
But you just improve on things until you try and get to what you believe to be truth.
Can I I forget the man's name, but a quite important statistician said that all models are wrong, but some are useful. Thank you, George Box. All models are wrong, but some are useful. And that's the tenets of which how science works. We can never prove something to be right. We can only prove what's wrong.
What we're saying is then, everything is just a theory. And it will stay a theory until something else comes along to replace it. So everything is just a theory, and that's the correct way of applying.
No, because once again, these are backed in evidence and they have utility. And that's all we can ever want of a model is utility.
Newtonian had that for 400 years.
And it works, and we were able
didn't
to,
work.
and we were able to construct bridges, we were able to do a lot of stuff on this planet using those ideas. And that's all we can have. Science, the big misconception is that science will never be able to give you the philosophical ideal of truth. It just is not what it's capable of doing. What science is capable of doing is giving you a model of which you are able to use and predict. That's all it will ever try to do, and it's doing it very well with the current model.
There are people out there who 20 years ago, when LIGO was like first in the pipeline, they were like, it'll never be done. You'll never see gravitational waves, and here we are, having seen them.
Just before, I just want to talk very, very quickly. Just one sec, mate. Just give me a sec. Just because I got the first 5 minutes. All I want to say to you guys was I agree with you, and especially about this misconception about a theory. The whole point is that you can make predictions. Yeah, Newton's theory, it was okay. It made certain predictions. Einstein's made a bit better. Something will come along and make them even better. Can I ask you why Ptolemy, from the 2nd century BC, was able to make the same astronomical predictions which stood for 1400 years before gravity, before a moving Earth, before a vast solar system, making all predictions of eclipses and all the predictions of the planets. He was able to do that 2,000 years ago before any of these, what I call newfangled explanations.
So Ptolemy was a believer in very much a geocentric universe, right?
Yes.
So, and also I believe that he thought every single orbit was a perfect circle.
Yep. But the point is that his predictions were accurate.
Yes, but
it was a model that worked.
Yeah, they became they're very complicated. So we can explain the orbit of Mars with one ellipse. I think he had to use almost 300 circles.
We don't see a perfect orbit. Our elliptical orbit. We still see retrograde motions.
Kind of that's the crux of my argument, that why would Ptolemy try to fit the orbits with perfect circles when they're demonstrably untrue?
His explanations were wrong, but his actual predictions, the theory was correct. Yeah. I still don't think you've got the explanation right, that's all.
Shut down.
Here we go.
Right, you mentioned detecting gravity waves.
Just before you continue, so Cardiff has a gravitational waves department. They get very angry if you call them gravity waves. Gravity waves happen on water, these are gravitational waves. I don't know the difference, but they get very bent out of shape.
The thing is, before I was into the flat earth and everything, I was really well into science, really into quantum physics, Einstein's theory of relativity, the whole works. So when LIGO, was it LIGO? LIGO, sorry, yeah. When they first started doing their experiments, I wrote to Ask a Physicist, and I asked them a question, and they weren't able to answer. Well, they refused to answer. Okay. I've asked the same question over the years to various people. None of them answered me. Okay. So this might get a little technical, just a little bit. Right. So the way LIGO works is that it's kind of like an L shape. Okay. With these 15-mile long legs. And what they do is they fire a laser, split the laser into 2 directions, okay, bounce them back off a mirror, recombine them, and you get an image on a screen, okay. Now, if at any time the distance between the 2 legs changes, So if a gravitational wave goes along one side, it will change the distance, change the size of that leg. Okay, then there should be an interference pattern on the screen.
Yep.
You agree?
Yep.
Right. So this is supposed to prove Einstein, but what Einstein said is that it's not the gravitational wave isn't in space; it's in space-time. So if space contracts, then time slows down so that the speed of light stays the same. So if you're doing an experiment with the speed of light, you will never detect gravity waves, because if the gravitational waves, so that if one leg shrinks slightly because of this gravitational wave, then time would slow down for that beam of light. So it will arrive exactly the same time as the other beam of light. No interference pattern. So if they detected something, that means Einstein was wrong. So if they don't detect something, that also means Einstein was wrong. So what do you got to say about that?
So leave it there. So that's the best answer today.
This would absolutely be the case if you were doing this experiment with anything other than laser light, or light in general. Whatever speed you're travelling at, if you were travelling at half the speed of light and you fired a laser, you would see that laser go away from you at the speed of light. Yeah. So it doesn't actually matter about the fact that the light is slowing down because it's still travelling at the speed of light.
Don't try and blind us with bullshit. The point is, you're using it. Well, Einstein says that it's not just space, it's space-time. You know, you change the space, time changes, so that the speed of light remains the same. That's the core of Einstein's relativity. Mm-hmm. So that means it can never detect a gravitational wave.
But the light is still travelling at the same speed.
Only because time is reciprocal to space. So it has to, according to Einstein, that's what has to happen. That's Einstein. It's Einstein. You can't argue with that. It's not me. It's Einstein.
It's not quite one over the other.
It is. That's it.
It is Einstein's theory. I'm afraid so. It described it accurately.
Okay.
Go and read it, and we'll see you next year.
It's still the beam of light is travelling further.
Sorry, say again?
The beam of light is travelling a different distance.
No, because again, it's space-time. Time and space curving, changing shape, contracting. But the speed of light has to stay the same in Einstein's theory. So, it works the same way in LIGO that it does apparently with the Earth.
Yeah.
Yeah. Yeah. Come
on. This guy's got to go. Chris is actually on schedule.
Weird science.
So, can I just say, on behalf of us at Flirt Earth, thank you very much. A big thank you so much.